We need to devote a bit of conversation to safety because it's obviously important. And we're going to start with by the consideration of designing unsafe circuits. And then I get into some of the more obvious forms of safety. Here I've got a circuit using a 12-volt power supply, a 4.2 volt lithium-ion battery, and a 39 ohm resistor to serve as to limit the current, and that current limit comes out to be 200 milliamperes. Now, typical lithium-ion batteries are considered to be fully charged when they're 4.2 volts plus or minus 50 millivolts. They're not like nickel metals where you can't tell the charge by the terminal voltage. It's very dangerous to overcharge a lithium-ion battery because very bad things can happen. Now, to kind of show as an example, this here is a level 1 prototype for a device I'm building. Presently working on the third prototype. I'm scared to death of this battery and actually built a little fuse into it by using 38 gauge wire. So if anything goes wrong, the wire melts. This is a quality battery and it has its own internal current limiting. But these can be very dangerous. I was looking for a battery, and on one data sheet, the company, the distributor who was selling it, stated that the data sheet may not be correct. Now, what does that tell you about something that can catch fire, like in a skateboard or whatever, possibly burn your house down or kill somebody? So when you're designing circuits, always take into account what it is you're designing. Know your components. Do your research. Use the internet, by the way, whose information is not always true, and figure things out. Think it through. The correct way to design this would be to have a voltage regulator sitting in here that would output nothing more than 4.2 volts and limit the current to something safe. So that's what I use in projects to date. It's not a very big device. Matter of fact, you can barely see it, sitting right in there in a SOT23 package. So be careful with designs. Don't do anything that gets yourself in trouble, and research parts if you're not sure how they work. Now, when it comes to safety, the most obvious problem has to do with capacitors that, well, kind of look like this guy. We see electrolytics in a lot of our lab experiments, and if you get the polarity backwards, and if they're at some operating current, they explode. Simply put, the ones we use in school or try to use have an X in the top of them, and what that's designed to do is to pop open and relieve the pressure. It emits a lot of nasty stuff, but at least it doesn't have metal projectiles. Non-vented electrolytics will explode, and it looks like a party favor going off with ejecta. Very dangerous. If you're seriously involved in electronics, you are going to blow something up. It happens. It's going to happen. What you need to do is be prepared for it. Now, the obvious safety issue is safety glasses. There's no undo button on a piece of something stuck in your eyeball. There are 10,000 80 seconds in a week. How long does it take to put on safety glasses? If you expect something to fail, when it does, you're not surprised. Now, to share with you some of my experiences might be insightful. The first happened when I was about 7 years old, and I took a fluorescent light starter. And inside of it was a little bulb that looked like a neon light bulb, and I thought it'd be cool to stick it in the wall and light it up. So I trimmed the wires off and tried to feed it into this outlet, and of course the wires weren't hardly long enough, and after I wiggled it around for a while, I in fact made connection. The resulting explosion melted the wires, scared me to death, and I jerked my arm away at 1,000 miles per hour, and my elbow hit a vise behind me. It really hurt. Second adventure is when I was trying to modify a dielectric heater, which is used basically to laminate the glue in between plywood. I had this thought of making popcorn, and this is pre-microwave oven days. So I had 4 huge transmitting tubes in a chassis with a work plate, looked like a V, where I was going to put a bag of kernels in there and expect it to pop. Well, I made a mistake, didn't turn off the power, and got a really bad shock, burnt my fingers, felt like Superman punched me in the chest, and heard a hum in my head. I later came back to measure precisely the secondary voltage of that transformer, and it was 1000 volts RMS and could deliver about 200 milliamperes. It was a miracle I wasn't killed doing that. Another example, I went to trim a tree, and not too long ago, a branch was growing out over the feed for our neighborhood, and we're way out in the country, and I didn't want to have a tree trimming service come in and cut the tree back real far. So I figured I'd just nip this little branch off before it got to be a problem. It should have fell and missed the wires. I'm on a 24-foot extension line with a bow saw, sawing this, and all of a sudden I let go of that saw. Something wasn't right, and I couldn't figure out what. I touched it again, got that buzzing feeling. So I'm balancing on a 24-foot extension ladder, wondering what I can touch. So I reasoned the ladder, touched it. It was, well, electrically high. I didn't feel a shock because it and I were at the same potential. But it was at some positive voltage because it was leaning up against the tree. Climbed down to the bottom, hopped off the ladder, went around and looked at that branch, and the tip of it was laying on that wire. Never expected that to happen. I could have been killed. Other examples. 2 years ago, working on a light-emitting diode, I needed a high-power infrared emitter. It was pushing 1 amp through, which is a non-repetitive current rating. Made a mistake and blew the thing up. The top dome of that is probably embedded in the wall behind me. Have no idea where it was. Fortunately, it didn't hit me, and I was wearing safety glasses. Then, this is a stroke of genius, somehow I got 120 volts across the voltage regulator. 5-volt voltage regulator. The package exploded, and I don't know where pieces of that thing went. High velocity explosions. When you're cutting wire, when the cutter cuts through the wire, it launches a small piece of metal, sharp as can be. And who's your lab partner? Even if you're wearing safety glasses and they're not, they're at risk. So when you cut wire with wire cutters, be sure you're holding on to the piece you're cutting off so you don't launch it across the room at some terrible velocity. The last example I'm going to give you, or second last at least, is I was cutting Romex one day, and this is the wiring in your wall, and this was fused to 20 amperes, and I actually double-checked this to make sure that I had the breaker on. Well, thought I did, got up on a ladder, cut through it, okay, 20 amp breaker, cut through the black lead hot and the white lead return, nice mini arc flash, blinded for a little bit there, scared the heck out of me, wrecked the pliers, melted a hole in the cutters. Needed to be safer, but at least I was wearing safety glasses so the metal, liquid metal, wouldn't affect my eyes. The most dangerous appliance in your house is a microwave oven. The transformer operates at thousands of volts. If it breaks, you can typically take the front cover off it and look for a fuse. Fuses wear out. Sometimes, of course, they blow up, there's an overload, but the element side of it expands and contracts, and sometimes it simply fatigues. So if you're changing a fuse in a device like a microwave oven, and if that fuse is brown, you be sure to change it with the same ampere rating and use a brown fuse. Here's the deal. If you use a glass fuse, when it fails, and since we're talking about an inductor which has a collapsing magnetic field, there are thousands of volts involved. And you can arc across the inside of that and it doesn't interrupt the circuit. With a brown fuse, it's filled with sand. As soon as it pops, the sand falls in between and quenches the flame. Microwave oven has 4 parts: transformer, capacitor, big diode, and a magnetron. It's a vacuum tube that looks like a diode. I don't have a piece of equipment in this house that can measure the voltages. I repaired a Maytag, failed, took the chance, had it on the counter. The only thing I could test was the capacitor. And I ended up buying a magnetron just on the hopes it was the problem, and it was, but I was truly scared. Remember that a capacitor, the energy W, equals 1/2 CV squared. That squared means a lot, and the energy here can do a lot of damage to you. Always be careful with capacitors. Further, some capacitors exhibit an effect called dielectric absorption. What that means is, if you take the capacitor and physically discharge it by connecting the leads together, and correctly, there should be some resistance in here, you may see a spark, and you think it's discharged, so you remove the wire, and you walk away and come back to this, half-hour later, the capacitor is partly charged again. Now, where I learned about this was in old picture tubes. They're terrible for dielectric absorption. You discharge a 25,000 volt anode on a CRT, which has capacitance, it's required to work, and you think you're safe, and you come back later and get lit up. I did that carrying one across the basement floor when I was in college. My parents hung sheets in the basement, and you'd have a dryer. The sheet hit the anode of the tube in my arm, and I'm juggling a 21-inch tube, which has who knows how many tons of pressure on it, because the inside is near a perfect vacuum. So, at all costs, be careful, be safe. Don't take any chances, because a lot of this you can't undo. You can get killed very easily if you're not attentive. In this course, we'll be working with raw AC, not even isolated, for certain experiments. So, as long as you use your head and you're safe, one hand please, all is well. Now, the last thing I'm going to show you is regard to getting a shock is I was repairing what's called a monoblock audio amplifier. This is a high quality vacuum tube amplifiers from the, well, it was invented per se, the circuit was invented in 1948. I'm going to show you what it looks like. So let me swing around here and point the camera down there a little bit. And there's our guy. You can see the filaments lit up. And these two guys here are the output tubes. They're quite expensive. And a capacitor failed inside of this. And I was repairing it, and somehow I had it turned on and was doing some tests, and I got my thumb from the chassis to one of the leads on these tubes here, and later I measured it to be 450 volts DC, which is much less dangerous than AC. It took 2-3 hours for my thumb to stop hurting. So, safety is not an option. Expect things to go wrong, and then when they do, you don't get hurt. And that's the name of the game. So thank you for listening. Every lab has safety glasses. And if you can't find a set, you tell the instructor and he'll get you a set. Don't take chances. Thanks for watching.